Welcome to this short talk about the basics of magnetism. This talk should serve you as a prerequisite for other talks you will be hearing during the workshop. And yeah, so my name is Robin Hilger, and I'm a PhD student at the PGI1 IIS1 at the Forschungszentrum Jülich. And first, we will discuss where magnetism is originating from. So we have two main sources of magnetism. One are moving charges, so currents, which cause electric and magnetic fields to arise. This is called electromagnetism then. The second main source of magnetism is the intrinsic magnetism, which is caused by the spin of particles, in our case electrons, which are of course contained in atoms and therefore give rise to magnetic moments in atoms. So if we're talking about magnetism, we always have to talk about magnetic fields and magnetization. So there are diamagnetic and paramagnetic materials, which is basically a way of describing the sign of the magnetization of the specific material. There are also ferromagnetic materials, which are materials which exhibit a magnetization which is present without any external fields. And of course, there is also an orbital moment caused by the orbital momentum of the electrons, which arises during this whole discussion. We can also remember that each electron is basically carrying approximately the same moment, the same magnetic moment, of course, which we'll be using later on. So, is magnetism a rare phenomenon? One could guess so. This is a periodic table where all elements are colored, which are in a magnetic state in their solid state. So if you have a solid of that specific material, then you would expect for the colored elements to have a magnetic material. So guessing by that, magnetism should be pretty rare. However, if you take only isolated atoms, the periodic table is looking a little bit different. Of course, this is the case because every non-completely filled shell has some spin, because there is an odd number of spins, and so they can't cancel out anymore. So yeah, from that, you would already expect that you would have quite some elements with some kind of magnetism or some degree of magnetism. However, if you also take into account Hund's rule, you also know that there are materials which exhibit magnetism more strong than others, because the occupation is very different for the elements. So if you have an exactly half-filled shell, you will actually see some stronger magnetism than you would see with a nearly completely or just barely filled shell. So what actually drives magnetism? If we take a 1D box and some states and a particle, as seen here. First, we can ignore any interaction. So we have just a free electron moving in a 1D box. Then we can quantify its energy, which is just the kinetic energy term, and we can put an additional electron there. So in principle, both electrons would be in the lowest energy state, so in the state n equals 1, with opposite spin, and they wouldn't bother each other. So if you now take into account interaction and don't have a free electron system anymore, of course, this interaction term here would cause the electrons to move in different states, because they're in principle repulsing each other. So the interaction is the part which drives the electrons from one state to another. So from n equals 1 for one electron and for n equals 2 for the other electron. And the non-interacting part is the one which doesn't drive them in different states. So basically the interplay of those both energy terms or contributions, the interactive and the non-interactive part, is causing magnetism, or is governing magnetism, to be correct. So the non-interacting part is the kinetic energy part, and the interacting part is called the exchange interaction part. So If we're now taking a look at the density of states, we don't have discrete atomic levels like in the 1D box system before. We have a continuous spectrum. So we have a continuous graph of states, or of a density of states, of course. And you can see that this might give rise to magnetism if you take into account that materials can have a density of states for a spin up and a spin down part. So if you now take into account that magnetization will create a magnetic field, then you can do some Taylor expansion. And if you do that, you will end up with an energy term, which looks like this. So you will have some basic energy state E0, and you will have an up and a downshift depending on your sign of your magnetization. So considering that, you will probably end up with some type of spin split. And this spin split is actually very well known under the name of the Zeeman term. So you will now have some spin state where you have a higher density of states and somewhere you have a lower density of states. Or in total, you will have more states in one spin states than in the other. Of course, using this spin split, you can calculate your total magnetization using the integral of the difference of the spin up and spin down density of states. If you integrate that to the Fermi level, you can express your total magnetization in terms of a function of the magnetization. So if you now express this function and use the Taylor expansion we saw before, you can achieve this integral. So this basically is a simple model where we use the Taylor expansion, of course, and is related to the Stoner model or the so-called Stoner criterion. If we now divide this function f of m by m, we can see that we not only have a trivial solution here, but we also can have other solutions which are then magnetic. Of course, this trivial solution is non-magnetic, entirely non-magnetic actually. However, there can be multiple solutions for a given Stoner parameter where your magnetic solution has actually a lower energy than the non-magnetic solution. So this would cause a physical system to not persist in a non-magnetic state rather than in a magnetic state. Of course, the criterion for such a solution would be that the derivative of this function f of m at the point 0 would be larger than 1. Additionally, typical values for the Stoner parameter are 0.4 to 0.5 electron volts. So after seeing those spin splitting, we can now compare the actual Stoner model to some existing DFT calculation. So if we now do a DFT calculation and calculate the density of states for both spin up and spin down, you can see here the red curve, which is the DFT calculation, and the blue curve, which is the Stoner model. You can see that the physics behind those two lines seem to be pretty well matched. Actually, if you look closely, you can see that the topology is, of course, a bit shifted and not totally the same, but it's still looking very similar. So it seems that those models achieve the same physical results, which is, of course, always good if you have consistency in your models. Of course, what we saw is that the kinetic energy favors non-magnetic states, which we already saw a bit hand-waving at the one-dimensional box model, and that the exchange interaction favors magnetic states. However, we are still doing DFT, so we have to come back to expressing things with the density. And in principle, you could use the electron particle density n to describe magnetic things, magnetic systems entirely. However, if you try to do so, you run into difficulties, as it's pretty hard to decode Pauli spinors into a non-vector quantity, let's say so. And so this gives rise to another quantity which is used additionally to the electron particle density, and which is called the magnetization density, which is then a vector quantity. So using the particle density of the electrons and the magnetization density makes the implementation and the usage of magnetism in DFT much easier. So after all those nice figures and hand-waving theoretical expressions, does it actually work is the main question here. And as you can see by the examples we have hand-picked here, it's actually working pretty well. You can see here some LSDA and some GGA calculations which are matching the experiment fairly well. Of course, you can not only have intrinsic magnetic moments caused by the spin of the electrons, but you can also have orbital moments which are caused by the orbital momentum of the electrons themselves. So including this orbital momentum, which is basically an expectation value of the orbital momentum operator, you can see that those moments are typically pretty small. However, we can also see that the theoretical predictions using LSDA are not so well matched with the experiment anymore as they were before. So yes, we don't match them so well, but they are also pretty small. So I think that's a trade-off one has to accept if you're doing DFT. So we have been talking quite a bit about magnetic moments now, and we have also been discussing ferromagnetism as the phenomenon of present magnetization without an external field. However, there are also antiferromagnets which have a total magnetic moment of 0. However, that's only because they cancel out each other. And there also are ferrimagnets which in principle do the same. However, one of the atoms can have a larger or a smaller moment than the other. And so you have a net moment which is larger than 0. So you have many different magnetic orders which are possible, including non-collinear magnetic effects and alignments. And this is also part of the outlook, which I will give you now. Because in the coming talks, there will also be included some information about magnetic moments directions, aside from collinear setups, as we discussed them just now. There also will be information contained about spin spirals and more about how local our moments are described, or how the local moments of our atoms are actually described, or the muffin tins, if you want to get specific, and not restrict to these labels of atoms. And this is quite an interesting topic, which I hope you will have a lot of fun with Daniel Wortmann.